This lesson is about solving problems by modeling them with sinusoidal equations and graphs. In this lesson, there are a few different examples of applications that would be periodic in nature and also sinusoidal. And so what we're going to do is either take a graph like this mine's on and write an equation for it, or take the information that we've been given, create a graph, and then from that, create an equation that we can use to answer the questions in the problem. So for this mine's on, I just want you to see if you can write the equation for this application based on the graph. And remember, there's four key elements in your equation. There's the amplitude, or the A value ultimately. There's the K value, which is related to the period. Remember, we have a formula for that. There's the D, which is the phase shift. And that's where you would compare it to a parent function and see if it starts at a normal starting point either on the axis for a sine curve, or maximum or minimum for a cos curve. And then the vertical translation, which is the C value, which is also the axis of the sinusoidal function around which it oscillates equally above and below. So go ahead and try to write this equation and then come back and see how you did. I want to identify the key elements in this graph. I'm going to put a line where the axis is. Then I'm going to identify the key features or the key characteristics of this graph. In this case, the amplitude goes from 4 to 8, so the amplitude is 4. The period of the graph, it starts here and then it goes through all its values and ends up here at time equals 20 hours. So the period is 20, and from that we can get the K value, which is what we need for the equation. 360 degrees divided by the period. 360 divided by 20. If we cancel the zeros, we get 36 divided by 2, so the K value here is 18. And then we know that the axis is at 4, so the axis is y equals 4, and that's also our C value. Now we'll go ahead and write the equation. Typically what we'll do, unless we've been asked to do otherwise, is we'll see which model is the easiest to work with. So in this case, I'm noticing that this graph starts on the axis. That's a sine curve. So I'm going to use sine to write this equation. Y equals, the amplitude is 4 and it's not reflected, so I don't need a negative. 4 sine, the K value is 18. And here we're talking about time or hours, so I'm going to use T. I could have used distance for the Y. There's no phase shift because it starts where a parent function starts. And the C value is 4, so we need to add 4. And so that's our equation for this graph. Now we could have written this as a cos as well, but we would have needed a phase shift. Now we'll go on and we'll look at a problem that has questions to answer, and it doesn't give us a graph. It's up to us to create the graph. So we're going to read this problem and get the key information that will help us to draw this graph. So Candace is holding on to the end of a spring that is attached to a lead ball. As she moves her hand slightly up and down, the ball moves up and down. With a little concentration, she can repeatedly get the ball to reach a maximum height of 20 centimeters and a minimum height of 4 centimeters from the top of a surface. The first maximum height occurs at 0.2 seconds, and the first minimum height occurs at 0.6 seconds. So in order to graph this, we need to think about our period so we know what values to put on our bottom axis here. So we see here that the ball reaches a maximum at 0.2 and a minimum at 0.6. So if you think of a maximum at 0.2 and we go backwards, we could think of a sine curve, right? So sine curve starts on the axis, a maximum down to the axis, a minimum, and back to the axis. So that part in the middle would be half of the curve. The other way of looking at it would be if you just started from this point 2 being the maximum, and you thought about going from maximum to the axis, and then down to a minimum, that's half of a coast curve. So that's half a period, because then we would go back up to the axis and up to a maximum. So this turns out to be half the period. That tells us that the period is equal to 0.4 times 2. So the period is 0.8. So we will have our graph go up to 0.8 seconds. So I have about 10 spots here. So we'll go up by 0.1, but I'll leave every other grid space empty so it doesn't get too crowded. 0, 0.2, 0.4, 0.6, 0.8, and we'll go up to 1. Looking at the heights, the maximum height is 20. So once again, looking at our spaces here, it looks like if we go up by ones, that will about cover the graph, not quite. And so once again, I'll skip every other one. So we'll go 2, 4, 6, 8. And it turns out it does just fit the graph. So there's up to 20. Now what we can do is go ahead and graph the information that we have and then fill in the rest knowing the pattern. So the maximum of 20 is at 0.2 and the minimum's at 0.6. Then we have a minimum of 4 at 0.6. Now I need to know my axis. It's halfway between 4 and 20. So we can work that out. We could look here and see if that's 16. Half of that's 8, so 4 plus 8 is 12, or 20 minus 8 is 12. Also, we could think of it as a formula, and we could say that the C value is equal to the maximum plus the minimum divided by 2, because it's in the middle, that's an average. So the maximum plus the minimum divided by 2. So what we have is 20 plus 4 divided by 2, and that's 24 divided by 2, so that's 12. And that's what we figured out just by looking at the graph. So our axis is right here at 12. Now I can finish the rest of this graph. Coming back this way a quarter, it would be at the axis. And then coming past this point, the next quarter which is in the middle of these two, would be on the axis. And then after this point here, the next quarter, we would be back to the axis again. And so we see that we've ended up at point 8, which is our period. And then there's a sketch of one cycle. And now we can use that to answer these questions that we've been given. First of all, it says determine the equation for the sinusoidal function that represents the height of the lead ball in terms of time. So this time we have variables given specifically h and t. So that's what we will use in this equation. I already have my c value. My a value is equal to 8 from 12 to 20, which we worked out earlier, half of the distance from 4 to 20. And there's no phase shift, so we don't need to be concerned about that. And I've made a positive here because this is not reflected. And we see here again that this is a sine curve. So what we have is h is equal to 8 sine. One thing I didn't work out was my k value. So the period we already learned is 0.8. K is equal to 360 divided by the period, which is 0.8. Now, if we want that as a fraction, we can multiply the numerator and the denominator by 10. This will make that 8. So we would have 3,600 over 8. And then we want to reduce that. Now you can work on your mental math and figure out the two numbers that go into there. Or you can also do it on your calculator. We can use the fraction button on our calculator, 3,600 over 8, and then press equals. And turns out that it goes in evenly anyhow, it goes in 45 times. So our K is 45. T, and then our C value was 12. So now we have an equation for this graph. Then it says determine the domain and range. The domain, in this case it's an application, we have time. So the lowest time that we would have is 0. We don't have negative time. So it's the set of t is an element of R such that t is greater than or equal to 0. There is no limit in the positive direction with our time. The range, which is the height, is related to the maximum and the minimum. So the range is the set of h is an element of R such that 4 is less than or equal to h is less than or equal to 20. Here it asks what the equation of the axis is, which we actually figured out already in order to do our equation. And what does it represent in this situation? The equation of the axis is y equals 12. And to think about what it represents, we want to come back and look at the question here. So Candace is holding on to the end of a spring that is attached to a lead ball. As she moves her hand slightly up and down, the ball moves up and down. So at one point, the ball would have been stationary, and then she's moving it consistently such that it moves equally above and below a point. So that point where the ball is at rest on the end of the spring would be this height right here, which is 12. This represents the height of the ball when it is at rest. The last question asks us, what is the height of the lead ball at 1.3 seconds? So what we want to do is use our equation and substitute 1.3 in for t and see what the height is. H equals 8 sine of 45 times t, which is 1.3 plus 12. H is equal to, make sure my calculator is in degree mode, 8 sine 45 times 1.3 plus 12. And then we will get a decimal answer for this one because it's an application. So that's 19.4 centimeters. Therefore, at 1.3 seconds, the ball is 19.4 centimeters above the table, or above the surface. Now, at this point, I would like to stop and just talk about something with regards to this K value. Previously, when I calculated the K value, I didn't put the units on there. I'm just going to rewrite what we did. K is equal to 360, and I'm going to put the units in now, in this case degrees, and then the period was 0.8 seconds. Now what I want you to observe here is that what we have really is a ratio. It's 45, or a rate, degrees per second. And what is significant about that is the fact that sine and cos functions operate on angles. And yet in this graph we have time. So what's occurring is that this 360 degrees, which is a full circle and one full cycle, is equivalent to 0.8 being a full cycle. So when we put a time in here, what's happening is this is a conversion ratio that takes how far along the cycle this 1.3 is. In this case, it's more than one cycle. And it converts this amount to an amount in degrees, which represents how far through a full cycle this 1.3 is, but it can be used by a sine or a cosine function. Looking at this next question. John is floating on a tube in a wave tank. At t equals 1 second, John reaches a maximum height of 14 meters above the bottom of the pool. At t equals 9 seconds, John reaches a minimum height of 2 meters above the bottom of the pool. Sketch a graph below which expresses John's height from the bottom of the pool with respect to time. So once again, you'll see a pattern here where we're given key values. And again, we're given a maximum and a minimum. And remember that from maximum to a minimum is half of a period. If you were to go from maximum to maximum, that's one full cycle, or from a minimum to a minimum, that's a full cycle. So in this case, we've been given half a cycle once again. In order to do the value on the independent axis, which is t, we need to look at where these occur. So at t equals 1 second, we're at a maximum, and at t equals 9 seconds, we're at a minimum. So from 1 to 9 seconds, that's 8 seconds is half of a period. So the period is equal to 8 times 2, which equals 16. And that is seconds. Looking down at the bottom here then, it looks like we have about 16 grid spaces available. I'm going to label these every other again. So 0, 2, 4, 6, 8, 10, 12, 14, and 16. And then this also goes up to 18. And this axis is time. And the other axis is height. Looking at the height, the maximum is 14. So I will label every other grid space here. 2, 4, 6, 8. That goes up to 18. Next thing to do is to put these values on. So at 1 second, I'm at 14. And at 9 seconds, he's at 2 meters. At 1 second, he's at 14. And at 9 seconds, he's at 2 meters. 1 second, 14. 9 seconds, 2 meters. And again, that's half a period. From 1 to 9, that's 8. So if we go 4, which would be at 5, he will be halfway in between. 2 to 14 is 12. Half of that is 6. So our axis would be at 8. Once again, we can do C equals the maximum plus the minimum divided by 2, which is an average. So that's equals to 14 plus 2 divided by 2, and that gives us 8. From 1 to 9, we said that was 8, half of that was 4. 1 plus 4 is 5, and that is at 8 when it's on the axis. While I'm at it, I'm going to draw the axis in. The next point, going 4 again, because this is 16, every quarter is 4. From 9 to 13, this would be on the axis. And then the next quarter, which is another 4, from 13 to 17, that would be at a maximum. So what we have is every quarter, I'm going to mark off the quarters here. Starting at 1, 5, 9, 13, and 17. We can see the 4 quarters that we talk about where there's key values. So this graph here starts at a maximum. The next quarter it comes down to the axis. The next quarter it goes down to a minimum. The next quarter it goes back up to the axis. and then it goes to a maximum. And there we have our graph. Now we're asked to write the equation in terms of sine and cos. So that means that at some point, we're definitely going to have to do a phase shift. I have my period and the C value. I would like my K value. K is equal to 360 divided by the period, which is 16. Reducing that, 8 goes into 16 2 times, and 8 goes into 360 45 times. So this reduces to 45 over 2. Now we're ready to write our equation. Looking here, we see that if we carry this graph on, it's not going to hit the axis at any of the key points because it's already at a maximum at this point, which is 1. I'm going to start with the cos curve since it's at a maximum. The height is equal to the amplitude from 8 to 4, that's 6. And it's not a reflection, so I will put a positive 6 cos of 45 over 2 t. Now I need to look and see, and we mentioned that there looks like a phase shift. Notice that it starts at 1. That's to the right, so we need to subtract 1 from the t and put a bracket around that. And now I will put a square bracket just to show that this is all the angle right here that goes with the cos. And then the c value is 8, which is our axis, so that's plus 8. Now, in order to write this as a sine curve, we need to find a spot on the graph where it starts on the axis, which is right here. I could go here as well. There are infinite number of equations that we could write using phase shifts because this would continue to repeat itself. I'm going to start right here and use this point, which is at 5. Now, in this case, for sine, that would be a reflection, so I will need a negative value in front. So h equals negative 6 sine, k value stays the same, 45 over 2. This time it will be t minus 5 plus 8. And there, now I've written this in 2 different ways, one with a cos and one with a sine. And then it says, use the equation to determine what John's height from the bottom of the pool is at 21 seconds, and to check on your graph to make sure it makes sense. So it doesn't matter which equation we use. We're going to put 21 into either one of these. We'll just start with the first one. H equals 6 cos of 45 over 2, t, which is 21, minus 1, plus 8. And then we simply need to put that in the calculator. Six cos 45 over 2 times 21 minus 1 plus 8. And that equals 8. So 21 seconds, looking on this graph here, from 17, 21 would be 4 more seconds. And remember, our quarters are 4 seconds each. So that's from here would be going to another key value. In fact, if we go another 4 seconds, we will be on the cycle where we come back to the axis which is 8, and that's the answer that we got. So that makes sense. Therefore, John is 8 meters above the bottom of the pool after 21 seconds. And I will leave the consolidation question for you to work on your own, and then to work on the practice.